Good morning, students. So we have come to the end of quantum mechanics 2, the last unit. So this is about classical fields and second quantization. Second quantization, immediately it makes us to think there exists first quantization. So immediately we think about the first quantization. So far we have learnt only first quantization. So whatever we have learnt so far, Schrodinger wave equation and some models, time dependent, time independent perturbation, and even scattering theory, and all those things, they come under first quantization, in which the mechanical particles are quantized. See, we know in Schrodinger wave equation, and of course we have used a Schrodinger wave equation using a wave function. We have obtained the energies. The energies are quantized energies. For a particular n, we will have particular E. For another n, we will have another E. So for all type of n's, we will have different type of energies. So energies are quantized, and this is for the mechanical systems. And for the second quantization, we are going to quantize the fields. So in the first quantization, we have already quantized the particle. Quantize the particle means out of particles we can have quantized energies and quantized momentum. Whereas here in the last unit, we are going to discuss about, we are going to quantize the field. So difference between particle and fields, difference between first quantization and the second quantization we need to have. And of course second quantization is very, very important, because in the last unit we ended up with creation and annihilation of particles using Dirac theory. And this exists only in the universe. Fields are there in the universe. You have fields means nothing but waves. Fields, we can define fields for a system in which we have infinite number of degrees of freedom. Infinite number of degrees of freedom means infinite number of particles. Infinite number of particles exist in the universe. So they come under fields. So we are going to quantize the fields. What is the meaning of quantizing the fields? We know that about magnetic field, electric field, electromagnetic field. So we know all such fields. For example, when you take electric field, out of which electric field we will get only electric field intensity, we will get it. Suppose we are going to take magnetic field, we will get magnetic field intensity. Suppose we are going for electromagnetic field, we will have vector potential and scalar potentials. So the values of electric field, magnetic field, vector potential and scalar potential are numerous. So they are all infinite values will be there. For that we need to quantize those fields. So we need to have some science quantizing those fields. But when you are going to take the Schrodinger wave equation, just take Schrodinger wave equation, in which, as I said earlier, in which we have obtained only quantized energies. But this Schrodinger wave equation exists in the surrounding, environmental surrounding. But environmental means what? So it is very clear, that the gravitation field. Gravitation field is a classical field. And light interacts with the matter. Light we have taken as a classical light. Whereas Schrodinger wave equation is quantum mechanics. Okay, so that is a semi-classical approach. So we can have gravitation field. Even for example, when you take potentials, these potentials in which Schrodinger wave equation we have used V operator. For energy operator we have replaced with the corresponding expressions. For the momentum we have used corresponding expressions for the operators. What about for V? We have not used V, as we have taken exactly from classical results. So we can say that this is a semi-classical approach. The first quantization is a semi-classical approach, we can say, because we have taken for potential, gravitation field and for light, all those things we have taken only from the classical results. So first quantization, in which only we have quantized the particles, mechanical particles. But whereas in the second quantization, we are going to quantize the fields. So there is a difference between first quantization and second quantization. Of course, there are some differences which we are going to see later, but before that we will discuss about the topics under this unit. So this is about classical fields. So whenever we talk about classical mechanics, immediately we will think two famous approaches. One is Lagrange and Hamiltonian formulation. So we know already. So here too we are going to use the same thing. We are going to have the classical field equations. One is Lagrangian equation, Euler Lagrangian equation. Another one will be Hamiltonian formulation, out of which we are going to get classical field equations. So this comes under quantum field theory, because we are going to use instead of q, we are going to use psi. See, classical mechanics, Lagrangian depends on q, q dot, t. So we know already. So all three are independent variables. Q, p, t, they are all independent variables. So instead of q, we are going to use psi, which depends on position and coordinates and time. So psi depends on r, t. So this psi is probability amplitude that will spread everywhere as field. So we are going to get the expressions, field equations under Lagrange equation, then Hamiltonian formulation. Then Noether's theorem, which says about the symmetry. Quantization of real and complex scalar fields. As I said earlier, so in Dirac space, we have creation and annihilation of particles. Those creation and annihilation of particles are numerous. We will have to use creation operators and annihilation operators. So we can't say it's a fixed numbers, we can't say, because creation means it will have increasing values, whereas destruction operator will have decreasing values. So the values will not be constant. It's not fixed values. Whereas we have learned the same technique, creation operators, in linear harmonic oscillator, in which the particles will be constant, fixed particles. Here the particles are numerous, infinite number of particles. However, we will get the results with some modification. We will get the same results as we have got linear harmonic oscillator. Okay. So quantization of real and complex scalar fields. So those fields, it can be either real or it can be complex fields, scalar fields. Okay. And creation, annihilation, and number operators. Already we learned number operators in linear harmonic oscillator. We are going to have the same results as we have got linear harmonic oscillator. Okay. So this is for the second quantization, quantizing the fields, and we are going to get the same results. Okay. Then Fock states. And we know that already Schrodinger equation and quantum mechanics 1 lives in Gilbert space. Gilbert space, in which we have already used some vectors, some harmonic oscillators, some Hermitian operators and Hermitian operators which live in Gilbert space. So this is finite. Whereas in Fock states, this is just infinite states. So infinite number of particles will be there, and we can say that the extension of Gilbert space is nothing but Fock states. We can say, as I said, Fock states in which numerous infinite number of particles will be there. Okay. Then second quantization of Klein-Gordon field. So we are going to discuss all the topics under the unit classical fields and the second quantization. Now before that, we need to have the difference between first quantization and the second quantization. So we need to have at least some knowledge about first quantization and the second quantization. So here we are quantizing the particles, and thereby we are able to get the quantizing energy and momentum, and even length also. So for example, when you take a particle in a box, length is also quantized, energy is quantized, momentum is quantized. So we have quantized the particles. Okay, for first quantization. Here we are going to quantize the fields. We are going to quantize the fields, and this field is represented in terms of probability amplitude. The probability amplitude psi depends on r, t, position and t. Okay. So what is the meaning of field here? This is a number of degrees of freedom. We are talking about number of degrees, infinite number of degrees of freedom. So infinite number of degrees of freedom means infinite number of particles exist. Okay. Here phase space variables are trajectory, because we will be talking only about a classical interaction. When light interacts with the matter, this light is considered to be as a classical light. Okay, so there phase space variables are trajectory, but here phase space variables are fields. Fields nothing but waves. Degrees of freedom are constant. So degrees of freedom are constant here. It's fixed. Number of particles in a mechanical system, any mechanical system, it's fixed. It's constant. Whereas degrees of freedom are large. So we can consider this as infinite. So there will be infinite number of degrees of freedom, infinite number of particles exist. The number of particles are finite in Gilbert space. So whenever we talk about first quantization, we will always think about only in Gilbert space. So quantum mechanics 1 lives only in Gilbert space. So this is just the extensions of Gilbert space. So here number of particles are finite, or so there's a mistake, infinite. Okay, there's a mistake here. It is infinite in Fock space. Here it is finite. Here it is infinite. Number of particles are infinite because creation and annihilation operators. It will create, the number of particles will increase. If it is destroy, number of particles may decrease. So we can't judge whether it is constant or not. We can't judge. Only thing is the particles will not be constant here. It will be more. It will be infinite. Okay, uncountable number of particles. So difference between first quantization and second quantization. So to put in a nutshell, we can say that here the particles are quantized. Here the fields are quantized. That's all. Fields are quantized. We need to know about, especially when Dirac space exists, there exists negative energy states. So we need to know about the electron and the positron, particle and antiparticle. We need to know. Okay, so that's why we are going to quantize the fields, and we are going to take all the things from classical physics, Lagrange equation and Hamiltonian formulation we are going to discuss. So classical fields and second quantization, the quantum mechanics which we have studied so far dealt with a single particle or with the systems having a fixed number of particles. Any mechanical system will have number of particles are fixed. Hence we are able to consider the models, quantum well problem, linear harmonic oscillator, hydrogen atom. So those models, process in which the number of particles remain constant. Okay. On contrary, some processes, for example, beta decay, positron electron pair creation, which occur at high energies, are beyond the scope of this formulation. Okay. So number of particles will be coming out as beta particles. So they will be as infinite. So there must be another formulation in which we are going to study about second quantization. In addition, in Dirac's theory permits the creation of electron-positron pairs, and the explanation of negative energy, as I said earlier, states using old quantum theory is not satisfactorily done. Hence, a new theory incorporating the above points should be developed, known as quantum field theory. So we are going to discuss quantum field theory. Okay. So the main difference, as I said, about the first quantization, dynamical variable, position, momentum, energy becomes operators. Those operators, they live in Gilbert space in first quantization. And of course, we will be able to get all the discrete energies of energy, momentum, even the well-width. Okay. And second quantization, here the wave function becomes field operators. Okay, we are going to quantize the fields. Property described by counting numbers of one particle states being occupied. This occupation of number of particles, say about Fock space, okay, which we are going to discuss later. Process are described in terms of exchange of real or virtual particles. So virtual particles are nothing but photons. So we have already learnt in Feynman diagram, virtual particles, about virtual particles. So classical fields. Under classical fields, we are going to discuss few things. For a mechanical system of particles, the generalized coordinates are finite. So to refer any mechanical system in classical physics, generalized coordinates are very important. So which is nothing but number of independent degrees of freedom are finite. So generalized coordinates, which is nothing but number of degrees of freedom. So the dynamical variables are associated with the corresponding operators in quantum mechanics with the commutating relations exactly like this. So this is your commutation relations. We know already QI, QK, which is equal to Pi, Pk, which is equal to 0. Suppose if it's Qi comma Pk, that will give you IH cross del k. So they will commute, they will not commute. Okay, they commute with each other and they will not commute. The Poisson bracket in classical equation is replaced by commutator bracket of operating in quantum mechanics, dividing by IH cross. So Poisson bracket, which we have taken from the classical physics, and we are going to apply the Poisson bracket into commutator bracket, divide by IH cross will give you in quantum mechanics. So that's the rule. Whereas the classical field has an infinite number of degrees of freedom. So here this is about the fields, these are the waves. So infinite number of degrees of freedom, and it is analogous to the system consists of infinite number of particles. So infinite degrees of freedom, which says about infinite number of particles. Field allows creation and annihilation of particles. That's why they are not constant. Okay, a field is specified by its amplitude. So very important thing. Here talking about a field, this field is represented in terms of psi, which depends on position and t, and of course r is continuous and it spreads all points of the space and time. Okay, so this is your field. What we call this is amplitude, or otherwise we can say this is field function. Field function, and as I said, it's a function, field function, which depends on r comma t. That's why second quantization sometimes it is called as functor. First quantization, what we call this as mystery. So first quantization, surely it will give us it is nothing but a mystery. Whereas second quantization is a functor. Functor means it's a function of position, time, even function of derivatives. All derivatives in the sense the function will depend on position coordinate as well time coordinate. Okay, we are going to see the amplitudes psi of r comma t play the same role as in the case of a field as a generalist coordinates qi. So instead of qi, we are going to use this one. This is in first quantization. This is used in second quantization. In the case of mechanical system, so qi is classical physics, we know already, but qi is replaced in terms of psi in first quantization. Okay. The amplitudes are independent of each other. The amplitude function psi of r comma t, which can be expanded in terms of expansion theorem. Okay, so this is the expansion theorem, which is given by this, and of course we are talking about infinite number of particles, and the summation will be replaced in terms of integration. So when you are going to integrate, that means its number will be infinite. Okay, so this is for the discrete. So if we are going to discuss from discrete to continuous. So expansion coefficients are the field coordinates. The amplitude psi of r comma t are known as field functions. The field equation relates psi of r comma t and its derivatives. It means all derivatives. That is, it depends on del psi, d psi by dx or d psi by dr and d psi by dt. Okay, all derivatives. So that's why I said its function, functor. The field equation is analogous to the equation of motion. Of course, field equation which we are going to see is exactly analogous to the equation of motion of any mechanical system. The field propagates accordance with the field equation. It propagates accordance with the field equation. The field is the carrier of energy, momentum, angular momentum, and other dynamical quantities. Now, this is the first question we are going to deal with. It will come under big question. We are going to deal with Euler Lagrange equation. So this is a field equation. We are going to derive two field equations. The first one is Euler Lagrange equation, and second one will be Hamiltonian equation. So two equations we are going to discuss, and we are going to discuss in this class. We are going to discuss only one equation, which is nothing but Euler Lagrange equation. So this is the outline. If we know this equation, we will get Euler Lagrange equation. It's very simple idea. So we are going to use Hamiltonian variation principle. First point, as we use always Hamiltonian variation principle in classical physics. Okay, so we are going to use this one. Our aim is to get Lagrangian formulation for classical field. Aim is to find out the field equation. Okay, and we know in classical physics, Lagrangian depends on q comma q dot comma t. We know already. But here Lagrangian depends on psi comma psi dot. Okay, psi dot in the sense it is all derivatives. Okay, all derivatives means we will have d psi by dx or d psi by dy or d psi by dz. So d psi by dr together we can write. So this is your d psi by dr and your psi dot will be d psi by dt. So your psi is there, then del psi is there, psi dot is there and t is there. So now we have four quantities. So four vector quantities. What is this L bar? L bar is nothing but Lagrangian density. So we are going to get the equation, field equation out of Lagrangian equation. We are going to use only Lagrangian density. Lagrangian density means the value of Lagrangian per unit volume. Lagrangian density means the values of Lagrangian per unit volume. So Lagrangian density. And of course we are going to use this least action, what we call this as least action, variational principle. We are going to use this one and we are going to get this one. Okay, we are going to have some modification. At the end we are going to get this equation. And this equation exactly resembles with the classical Lagrange equation. Only thing is this has two terms, this has three terms. Because L depends on q comma q dot comma t. All are independent variables. Q comma p comma t, they are all independent variables, whereas psi all dependent variables. Psi, del psi, psi dot comma t, dependent variables. So that's the reason that extra one term exists. That's the reason. So that's the difference. Okay. So now we are going to discuss in detail about Euler Lagrange equation.